So I'm Meir Maor from Spark Beyond. At Spark Beyond, we try to automate data science. We try to find automatic insights in data and transform raw data into valuable insights. This is not what I'll be talking about today. Today, I will be talking about the difference between the classical machine learning predictive analytics problem of predicting the future and actually affecting the future. How we try to find the best way to take action, because we don't want to blindly know what's coming. We want to change it. We want to make the future better. That's why we try to do things. And this is very different, I will show, from a standard predictive modeling problem. We will talk about randomized studies and how they're the standard solution for the problem. We will show how they're not always viable. We will discuss some well-researched and less researched solutions for how to make do without them. And we'll do this with a few guiding examples. We'll start with Gro. Gro, as you may know, after failing to steal the moon, changed to be a data scientist, and he has a very common problem of reducing churn. So his standard approach is train a model, find those most likely to risk to churn, then apply some preventative action on those with the highest risk score, and lose lots of money. And the question is, why does this amazingly accurate model cause us to lose money? And the answer would be they're working on the wrong problem. We're trying to prevent churn, not predict churn. So there could be various segments this model finds. Maybe the model is telling us users more than 75 years old whose activity dropped are going to churn. These users are likely to churn because perhaps they just died. Any preventative action we try to maintain this user is going to be futile, and on those which did not happen to die, we're just giving them discounts or working for no reason. It could be that, so some people who are likely to churn are not salvageable at all. Others may be salvageable, but only with the correct action. We need to match the right action to the right person. If a person isn't happy with the service, giving him a discount isn't likely to help. Maybe it will even hurt. Maybe it will remind him there are other options out there, and we will actually induce churn by sending him a coupon. So we need to match the right thing. So we need to define the problem correctly. We need to predict the effect of actions. That's the first thing we need to remember. We need to define the correct problem. It's not about predicting the outcome. It's predicting about the effect of actions. So we need, obviously, to have past data about actions. If we never did any kind of preventative actions, we have little hope of being able to train a model which will predict the effect of new actions totally different than anything we've ever done before. And we need to remember the basic assumption of machine learning is, one of them is, we have a stationary distribution. We have a basic stationary distribution, so past distribution and what we're going to test on comes from the same data. And this is a lovely assumption if you're in the academia. The problem is it doesn't actually hold. In particularly, it by definition doesn't hold when we want to affect it. I do not want to take actions in the same way as we did in the past. So by definition, by changing the way we're acting, we are changing the sample distribution. We need to be aware of the fact anytime we're trying to take action, we have a transfer learning problem, and we need to be aware of the gap between the past data we're training on and the data we're actually trying to predict on, which is new actions, not the same, because we want to change the future. We want to do not maintain the past distribution. We don't like the past distribution. So the easy way out of minimizing this transfer gap is we do a randomized study. We take a subset of the population, we act randomly. This works very well in ad tech when we have many tiny actions with low costs. So we take a small segment, we'll serve randomly, we'll learn only on the random segment. We won't learn from the segment which was not in the randomized study. And then we believe we will have common support. We will be able to get a reasonable prediction for any action. Then we have a new user. We predict based on the randomized study. We get good results. However, in many cases, what we discover is we have a problem. We don't have a randomized study, or we can't do any significant size randomized study, and we need to work with past data, with observational data, which was not controlled. So can we learn from observational data without a randomized study about the effect of actions? So the short answer is no, you cannot. It's impossible. The longer answer is, well, sometimes. And a key requirement, we're adding an extra assumption, we no longer in the previous set of assumptions, is we have common support. Common support means for any individual, for any sample, patient, customer, be whatever we're predicting on, we want to have past examples which were similar to it, which were acted on in both ways, or in more ways if we have more than two actions. So we need to find. So obviously I gave a bit of a fuzzy definition here. Similar, how similar? Because no person was acted upon in two different ways, and no new example. So we need to have a notion of common support, of past evidence to support every action we want to produce predictions on, and not only a single action. Because if tall people always get a discount, and I learn from that, and comes a tall person and I want to ask, what will happen if I give him a discount? No problem. What happens if I don't give him a discount? Well, never did that to this person. I did that to other people, but never to the kind of person which is standing in front of me now. And the problem is, a machine learning model will give me a prediction if I just train to predict the outcome. It will not be valid. I cannot make any meaningful statistical statements about the accuracy of that model in such a scenario. In order for it to be accurate, we must have common support for any action we want to consider. And the question is, how do we know? Do we have, for a given individual standing in front of us, common support? So the trick is, we'll introduce the concept of a propensity model. For propensity model, what we're actually doing is we're modeling not the outcome, not will the patient get better, or will I make lots of money, or will the account churn. We're not modeling that. We're modeling past actions. Did I give him the coupon? Did I call to tell him? Did I give him this medicine or that? So I'm modeling my past action to understand whether or not I have support for my value model. So I build a propensity model which will tell me if a given prediction for a given patient should be trustworthy. If for a patient which I come now, I know in the past people who are like this were always treated in a certain way, then I will not have support and cannot trust the predictions for any other action. But if there's a certain inherent randomness and a certain segment and a certain portion, there's maybe it's a high probability for one, but a reasonable probability for the other. There's enough support, there's a non-zero probability for any action in the past, then we will be able to trust. Then we're close enough, at least for a certain person, into we're close enough to a randomized study. Now, in order to do this kind of propensity model, we need to add a new assumption. The new assumption we need to add is no unmeasured or hidden confounders. a confounder is something which is affecting both my past action and the outcome. If tall people were always acted upon in a certain way, and them being tall also affects the outcome, will the patient get better? Will the customer churn? And I don't have this information in my data, I don't have this feature, then I will not be able to properly control for it. So I have to assume anything which affects both action and value is in the data and accounted for, and the propensity model can capture it. If this is not true, then the propensity model cannot capture it, and I will erroneously think I have common support when in fact I do not have common support. Now, in reality, we can never be sure this is the case, except with a randomized study, but we still can get value by making this assumption without it being perfectly true. Now, what we're realizing is that when we're building a propensity model, unlike a normal model where we're hoping it to be accurate, with the propensity model, we're hoping it will be inaccurate. We're hoping for as many examples as possible for a large segment of the population. It will say, in the past, I don't know what you did. Maybe it's 20% this action, 80% that action, but not 99%. That's what we're hoping will happen. We're hoping for most actions. Because if for almost everything I know, if my past actions were entirely deterministic by things which were potentially confounders, then I'm back to square one. I'm back to the answer, which is I can't learn anything. I can't say anything about the action not taken. So we're hoping the past actions were close enough to random, were not entirely deterministic, or for at least majority of the population. It's okay to be able to say, well, for some people I don't know the answer, but for most people I do. That can be a valid result. So if we have a model and it's too good, then the answer is, can we make it weaker? And a key way of making it weaker is by removing features. We look at the top features and we're saying, okay, is this feature likely to affect the outcome? If we can confidently say that it affected my past actions, but I'm confident it does not affect the outcome, it is non-confounding, then we can exclude it from our propensity model, weakening the propensity model, increasing the range of people where we have common support according to our model, and being able to create statistically valid predictions for a larger portion of the population. So, for example, we have a doctor and he prescribes medicine A or medicine B. And we discover that where the doctor was trained is a key predictor in which medicine he gave. Now, if this is the only decision that doctor made for the patient, then we can be reasonably confident that it did not affect the outcome beyond the decision of the medicine, which is what we're trying to model, and we can exclude it. If, however, this doctor did many other treatments, and we don't know how they affected the treatment, then we will not be allowed to exclude where the doctor was trained as a non-confounder, because it could have affected the outcome beyond the action we are trying to isolate. And the answer would be, you can't do anything because you cannot isolate the action, and you must do a randomized study or collect other data in order to create a prediction. We'll take a more complicated example. Let's say we want to build new stores or dig a new well, or any such example where we have very expensive points. We have a handful of examples. We have maybe a few hundred, maybe a few thousand. Each of them costs millions of dollars. An unconventional oil well will cost $8 to $10 million. A store will cost $500,000. we can't do a randomized study and start building randomly. And the past decisions were very far from random. Smart people worked hard in deciding where to build and where to dig every one of these. And we want to recommend new ones. But how do we do that? We don't have a clear propensity model. There's also it's not a discrete action. There are many different choices. So if we want to do a propensity model, we want to know where is our value model action. We want to model the store profitability, or we want to model well oil production. We need to know when is it modeled, when do I have common support and when I not. But for the propensity model, we need negative examples. And there is an endless supply of places and configurations where we did not build a store. And then we need to use those. So we have an endless supply of places where we did not build a store. We never built a store in the middle of the ocean. And if we just use random points for negative examples, we will discover it is trivial to create a perfect propensity model which separates everything. So we want to create a better background, or we want to filter it. And evidently, it's okay to have background which is pretty poor. It's okay to have poor background, because if I generate tons of data and I filter as obviously things I would never build in the past, if I filter 99% of them, but I'm left with a tiny fraction of a percent, but still a significant number of examples which I cannot say I would never have built there in the past, and they're still diverse, they're not in the same locations as the past, then these are valid candidates. These are candidates which I should consider. These are candidates which, if I build a model on past data to predict the profitability, I'm going to get a statistically valid answer for those examples which are inseparable from the past data. Now, this idea of generating noise, generating random data and filtering it, and maybe improving the past data should be familiar to you in a form of GAN, of a generative adversarial network. I see the slide isn't working. So in an adversarial scenario, we have a generator which tries to generate noise, and we have a discriminator as before, trying to decide is it noise or a real example. And we have a feedback loop to make the generator better. This has been very successful in a variety of image trainings, but it's also valid over here. Now, one of the problems with using these deep learning style techniques is we typically have, it's expensive data, so we don't have a lot of data. And one of the key problems is that you have the generator can encode the training data, even if it doesn't see them directly. And it will start producing candidate examples which are essentially the same as trained examples. So we need to impose diversity. Now, defining diversity is difficult in the general case, but in the examples I gave, and I assert that they're a common case, we had a key attribute. We had a location as a key attribute. So by simply imposing diversity only on this one attribute, even if a store has many other attributes we should consider, size, number of employees, storefront, we can just impose diversity only on one attribute, and if it's diverse on that attribute and still inseparable from the past locations, then it's a valid candidate to consider. And if we score it with the value model and choose the best one, we're likely to get good results. And choose the best one, choose where to build a store, where to dig a well. We'll take a more difficult example. In some cases, we have past actions were entirely deterministic. We know for a fact how we made decisions. It's based on a confounder. We were choosing the price of a product based on how the average income in the neighborhood. And we know it's a confounder. We can't exclude it. If we try to build a propensity for where we did it, we'll get perfect separation. We know how we gave everything. And the question is, in such a case where the rich neighborhoods got one price and the old neighborhoods got another price, can I say anything about price sensitivity? Can I learn how does that affect? Now, based on what I said previously, I would say the perfect separation, it's a confounder, I can't exclude it, would answer no. But we have another trick up our sleeves. We can impose a smoothness assumption. We had a past decision, and we had a discrete decision boundary, which we decided, and it was arbitrary. We decided what the threshold between rich and poor. So if we focus on the decision boundary, we look at neighborhoods which were only mildly rich or only mildly poor, and we compare them, then we assume that the difference in income is not important, and the only difference is the action we took. So on these examples, we can focus. This is similar to an approach, a classical approach of adding a smoothness assumption is to jitter training data. If I would jitter the income data before training my propensity model, I would get on that boundary, I will get a non-zero propensity for both actions, because it wouldn't know if it's the jitter result or not. So adding smoothness assumptions and jittering data is a neat trick for solving this problem and getting some value even out of data which was in the past entirely deterministic. The last topic is going to be evaluating. So we want to be able to evaluate our model on past data. Now, the easy option is if we have randomized data again. So if we have even a small amount of randomized data, not enough to train a reasonable model, but it may be enough to evaluate it. So we have several policies of taking actions, and we want to evaluate them. So we will evaluate each policy only on the subset of data where it matches the randomized data. And if it matches, then we have a valid, and it's statistically valid, and we know how to evaluate how good the new actions are. And this is essentially equivalent to doing a future study. And if the small data is random, then we know that it will have support for any possible strategy of action selection. If we don't have even that, then we need more assumptions if we want to do evaluation. If we're taking the site selection example, then we may want to not do the noise generation, but simply score candidates produced by the past process and only filter out the less good ones. So then we want to assume that there are more locations like the mid-range, at least, stores. And then according to how aggressive we're filtering the candidate stores by the value, this assumption may or may not hold. If we're only throwing out from 10 candidates of potential stores, and if I'm only kicking out the worst one, then the chances are the next one up I'll bring in instead of it, the chances are it will be at least a medium range store based on past performance. But if I'm gonna try kicking out 90% of the data, then assuming I still have that many extra candidates, or assuming that I have more candidates like the past, will no longer hold. In general, we have to take an extra leap of faith if we're doing an evaluation like that without randomized data. So you always have to do a bit of hand waving or do the best thing, future testing. Go and build a few stores. And that's it. Questions?
Any questions, anyone? What does Spark Beyond do?
So, Spark Beyond tries to automate machine learning. It tries to automate the process of taking raw data, as it's in the wild, text, geospatial, whatever, and find how to transform it among itself or by cross-referencing it, possibly with external sources, in order to find insights, in order to create insights and simple, explainable models, which are also useful for what I discussed now, because a key aspect in the actionable thing is understanding the insights, understanding the features, which you can do with models like Spark Beyond produces, but not if it's only a pile of coefficients.
Hi. Could you elaborate a bit more on your argument that when a model is very well defined, we should strive to make it weaker?
Yeah, if the propensity score is perfect, if I can always tell, given a customer, for example, whether or not I would have given him an action, then I know I do not have support for the alternative action. If the propensity model gives perfect separation, that's proof of lack of common support. And therefore, I know if I know to determine the past action, I know the alternative action has no support, and any prediction I make on what will happen in the alternative action has no validity at all.
Thank you again.